Okay, can we all see the screen now? Is the screen better? Let me see. Are we all seeing the screen?
No, sir.
Oh my. Okay, if it's refusing, then we'll use a WhatsApp call if this is denying. How about now?
Yes.
Okay. All right. So where were we? So I was just giving you the formula, and then we're just reading the question. Okay. So if you're seeing the screen now, it's okay. Are others also seeing the screen?
Yes, sir.
Yes, sir.
Okay. All right. So we want to answer this question here. We're going to follow the same steps that I have shown you. Okay. We're going to follow the same steps. So let us just begin now. I'm going to draw a beaker now. I'm going to draw a beaker. I'm going to draw a beaker now. Yes, I'm going to draw a beaker. Draw a beaker. I'm going to draw a beaker here. In this beaker, guys, what are they telling you? So I want you to think like that in the exam. What are they telling you? They're telling you that there is a 13 gram of impure sample. You see this? You see this information that they're giving you here? A 13 gram of impure sample of the potassium hydroxide. That's the information that they're giving you. So is initially dissolved in 200 cubic centimeter. Okay, they're adding an impure one, the one that is not pure. We know what's going to happen, right? We know what's going to happen. Only the pure is going to react. We know that information, right? Because I've told you that we only use the pure one. So this is what is happening here. I've got my acid here, which acid are we talking about here? The nitric acid, HNO3. That's the nitric acid that we're talking about here. So my nitric acid, this is my nitric acid here. All this here, this is my nitric acid. This is my nitric acid. And then what am I adding? They're saying they're adding what here? 13 gram. 13 gram of who? 13 gram of who? Of impure. Okay, 13 gram of impure sample of potassium hydroxide. So that's what they're adding there. 13 gram of impure potassium hydroxide. And we only know that from this impure, only the pure will react. The pure one of potassium hydroxide will react, but the impure one won't react. Only the pure will react. Okay, so if you are no longer seeing the screen, you must say it. Ne? If you're no longer seeing the screen, right. So we're adding this amount here. 13 gram of impure. Of what? Impure. Potassium hydroxide. That's what we're adding there. Okay. And then what else are they telling us? This impure potassium hydroxide is initially dissolved in 200 cubic centimeter of 1,2 mole per cubic decimeter nitric acid. So this nitric acid, we're given the volume and its concentration. Okay. So what we are seeing here, the 200 cubic centimeter is our volume, and the 1,2 mole per cubic centimeter. We know that those SI units symbolize concentration. So we're given concentration there. That's all we're given concentration. So we're given volume and concentration. So this beaker has the volume. This beaker has the volume. Are you still seeing the screen?
Yes, sir.
Okay. So I can just continue, sir. So now, this is what is happening here. So this beaker has 200 cubic centimeter, all right, of what? Yeah, this one is the volume here, which is the volume. That's the volume. Yes, volume, but this is the volume of the nitric acid. Volume of HNO3. That is its volume there. But we're also given the concentration, right? We're also given the concentration. The concentration we have got 1,2. 1,2. Is it 1,2? Yes, if you look carefully, there is 1,2 mole per cubic decimeter. It's 1,2. So it's 1,2 mole per. Oops, this thing. Per mole per cubic decimeter. 1,2 mole per cubic decimeter. That is the concentration. Okay. This is the concentration of HNO3. This is the concentration of HNO3 there. Concentration is those square brackets, guys. Symbolize concentration. Okay. You learn it in chemical equilibrium. That the square brackets symbolize the concentration. And here, this is the initial concentration, the concentration that we had in the first beaker. Okay. And the volume that we had in the first beaker initially is 200. Okay. So anything in the first beaker, guys, is initial. It's our initial. So master that. Okay. So what happens next, guys? So we know that only the pure will react. Eh? The pure potassium hydroxide will react. Then, yes, all the pure potassium hydroxide will react, which means the potassium hydroxide will become the limiting reagent. So this one is the limiting. It's the limiting, this one. So the pure potassium hydroxide is our limiting reagent, which means it's going to react completely in the beaker. It's our limiting. It's our limiting reagent, okay? But how about the nitric acid? Is going to remain in excess, right? So the potassium hydroxide will react with the nitric acid. The nitric acid will be eaten away, but only a small amount of the nitric acid will remain in the beaker. It will remain in the beaker. So let's draw another beaker now. So drawing a beaker will help you guys. It will help you. Okay. So this is another beaker now. In this beaker, we have this. In this beaker, we have this. In this beaker, we have that. the nitric acid that is remaining. Okay, this is HNO3 remaining, which means it's in excess here. Excess HNO3. Okay, some of it has been neutralized. Okay, we only want the excess. So we're going to take this excess. I want you now to read the statement. Look at the statement now. They're saying the nitric acid was in excess. Yes, we know that it was in excess. I gave you a trick just before we began this question here. I said the one that appears twice in both equations, equation A and B, is the one that is in excess. Okay, I told you. So the nitric acid, yes, is indeed in excess. Then what are they telling you in the second statement? In the second statement, they're saying 50 cubic centimeter of the resulting solution was titrated to neutralization using 23.67 cubic centimeter of a standard solution. So we're given the standard solution here. We're given the standard solution. I told you about the standard solution. It is the one that we put where? It is the one that we put in the burette. Okay, but let's see how that works. Sodium. So the standard solution here is the sodium carbonate solution. Okay, so the 50, I want you to look at this 50 here. 50 cubic centimeter of the resulting solution was titrated. So we are only taking 50 here. Let's take the 50. You see the one that is in excess here? It is 50 cubic centimeter in excess. So the one that is in excess here, it is 50 cubic centimeter. They are only taking 50 cubic centimeter of the resulting solution. Resulting, which means the one that is in excess. Okay? The one that we are left within the peak, which is in excess. This 50 cubic centimeter, we're going to take it now. Let's take it. We're going to take it and we're going to what? Titrate it. Now there's going to be titration that is going to be involved. Titration. We only take the one that is in excess, guys. But what's the amount? What's the amount that is in excess here? The amount is 50 cubic centimeter. Was then titrated. We're titrating this 50 cubic centimeter of the excess nitric acid. Okay, of the excess nitric acid. So let's titrate this. Now we involve titration now. So now there's titration involved. In titration, I showed you that there can be what? A burette stand here. You don't have to draw all this in the exam, but it's going to help you. Okay, it's going to help you answer the questions. So we know that there's a burette here. Is a burette. And in this burette, there's a beaker. There's a beaker, of course. And this beaker, I said there's what in this beaker? I said in this beaker that I'm going to draw now, this is my beaker here. This is my beaker. This is my beaker. In this beaker here, guys, let me do this. Let me increase my beaker here. Yes. In this beaker, there's someone whom we're adding here. There's something that we are putting. I said we are putting what here? The standard solution. The standard solution is the one that is going to enter here. Okay? It's the one that is going to enter. Because at the bottom here, we were having the nitric acid, the excess nitric acid. So the excess nitric acid, we just took the 50 cubic centimeter of the nitric acid. So what we're having here is the nitric acid. That nitric acid is in excess. HNO3, right? Let me do this. HNO3. This is a nitric acid in excess. And it's 50 cubic centimeter. It is 50 cubic centimeter. We're going to titrate it with the standard solution. Our standard solution is the one that we're given the known concentration. Can you see? This burette has a standard solution. And that standard solution is the sodium hydroxide. Am I correct? Let me see. Look at what the statement is saying to you guys. They are saying 23,67 cubic centimeter of a standard solution. I'm reading this part. Okay, I'm reading this part here. Can you see this part? 23 cubic centimeter of a standard solution of 0.85 mole per cubic centimeter. Can you see that this standard solution here, we're given concentration? I told you that the standard solution, they give it the concentration. We know the concentration. And this standard solution is sodium carbonate. So that standard solution is here. It's in this burette here. It's inside here. So let me even indicate here. It's inside here, this sodium carbonate. Okay, it's inside here. We know its concentration. It's inside there. So this standard solution is sodium carbonate, right? There's a standard solution. There's a standard solution, which is what? Sodium carbonate. We know its concentration, correct? So we're going to use this concentration here to get the concentration of the excess 50 in 50 cubic centimeter, because we don't know the HNO3, the nitric acid. We don't know its concentration. The concentration of the nitric acid, we don't know it. But we're going to use the standard solution to get the concentration of what? Of that nitric acid. This is good. Okay, this is good. So these drops here that you are seeing, guys, usually in titration, we control them. We control these drops here using something like a tap. So it's something like a tap that we use to control this thing. Okay, so we control the drops so that it reaches the end point. It doesn't surpass the end point, right? So that it doesn't surpass the end point. So we continue dropping these drops here, just putting drops. We can't just put everything inside the beaker. Otherwise, it's going to change the color. We won't get the color that we want. Okay. So far, guys, to summarize this question, we're given 13 grams of impure sodium hydroxide. Okay, only the pure will react, the pink one, right? But when we know that the pure one will eat away the blue one, which is the nitric acid, Okay, it's going to eat it away. But we know that some of it will be left in this beaker here. It's going to be left in this beaker. The nitric acid is in excess. And the one in excess is 50 cubic centimeters. They are saying to you, this 50 cubic centimeter, we are taking it, we're going to titrate it. So we put that 50 cubic centimeter in this beaker, then we put a standard solution, then we put drops, okay? Let's get this excess nitric acid in 50 cubic centimeter. Let's get it now. So that standard solution, let me even indicate here. Let me even indicate here. This will help us. Let me put it in brackets. Here. This here, this will help us. This standard solution, guys, will help us get concentration of HNO3, because we don't know its concentration of HNO3. It will help us get that concentration. This standard solution. Okay, so I think that was an important thing to highlight. Very important thing to highlight. Okay. Now, we have that information. I said the standard solution will help us get the concentration of nitric acid. So let's get that concentration of nitric acid. Let's get it. Okay, let's get it. So I'm going to say now, with the standard solution, I'm given the volume. Can you see with the standard solution, guys, I'm given the volume and the concentration. So in order for me to get the concentration of the other, I will need to do this. Firstly, this is going to be my working here. Let's work. So I'm going to say now, first step. This is my first step. I'm going to get the number of moles of the standard solution, guys. I'm going to get the number of moles of the standard solution. Number of moles of the sodium. Oh, it's Na2 here, please. Don't forget, it's Na2 here. Don't make that mistake. It's Na2 and then a carbonate. Okay. Na2, then a carbonate. So it's Na2. Okay, then a carbonate. So these are the number of moles of sodium carbonate. All right. Is equal to CV. You know that the number of moles, guys, to get the number of moles, is just concentration times volume. Then we just substitute, right? We just substitute. What is our concentration? What is the concentration of? That is, I want to test if everyone is hearing me. Guys, what is the concentration of the sodium carbonate that we're having here? I've highlighted it in yellow. Okay, yeah. What's that concentration?
23.67 cubic centimeters.
But the 23.67 cubic centimeter is the volume. Can you see? The concentration is what? What is the concentration? We're given the concentration. What is the concentration? 0.85. 0.85. Remember, concentration is the moles per cubic decimeter. The 23.67 is the volume, all right? But the 0.85 is the mole per cubic centimeter, which is the concentration. It's a concentration 0.85. So 0.85 is our concentration. So let me substitute there. 0.85. So it's 0.85 here. And what is our volume? Our volume is the one that is here. So it's 23.67. 23.67. Yes. 23.67. But remember, it's centimeter cube. I want it to be in decimeter cube. So what do I do? I divide by 1,000. Remember, in grade 11. I divide it by what? By 1,000 to get to cubic decimeter. So I divide by 1,000 there. So what are the number of moles? I'm only looking for the number of moles of sodium hydroxide, of sodium carbonate. Okay, it's the standard solution. It's the standard solution. So 0.85 times 23.67 divided by 1,000. I'm going to get here 0, please use your calculators. You must make sure that you take out your calculators. 0.20 1195. These are in moles, guys. These are moles because we're getting the number of moles, right? We're getting the number of moles. Okay. Yes. So, guys, I want to ask from you. Now, I want you to focus on titration. Focus on titration only, guys. In this titration, I've got the standard solution, which is concentration. All right? It has concentration and the volume. I have now the number of moles. Can I get the one in excess, the nitric acid? Can I get the number of moles of the nitric acid? Yes, because in titration, I'll be looking at which equation? The titration equation, guys, is equation B. Look at equation B, guys. That's your titration equation there. 2HNO3 plus Na2 carbonate. Equation B is our titration equation, okay? So I'm going to take this titration equation. So in this titration, let me highlight here. Titration, this is equation 2. I'm even highlighting it there. It's equation 2. So what is our sodium carbonate reacting with? It's reacting with nitric acid. So I'm going to put stoichiometric ratio here. Let's put our stoichiometric ratio. I have the number of moles of sodium carbonate. Do I have the number of moles of nitric acid? No, I don't have. Okay, so I'm going to do this now. I don't have, guys, so I'm going to do this. Therefore, HNO3 is to what? Is to sodium carbonate. Can you see that? I'm doing stoichiometric ratio now. We're doing stoichiometry. What is the number of moles of sodium carbonate? In equation 2, guys, what's happening is titration. That is the equation for titration, please. So, in equation 2, sodium carbonate is 1. So it's 2:1. It's 2:1. 2:1. 2:1. So, here, I'm going to say here it's 2, here it's 1. What are the number of moles that are involved in titration? What are the number of moles of sodium carbonate? I want you to do this now. Sodium carbonate. Look at the number of moles of sodium carbonate. What are they? We just got them now. These are the number of moles. It's 0,020, 1195. Okay, 1195. We don't know the number of moles of the nitric acid. So we multiply them by 2 there, cross multiply. So we're going to say the number of moles of HNO3. Our goal, guys, is to get the concentration of HNO3. Our goal is to get the concentration. For now, we are only getting the number of moles. But who is helping us to get the number of moles? It's a standard solution. That's why I told you how important the standard solution is. It helps us to get the concentration of the unknown. Okay, so the HNO3 doesn't have the concentration, so we want to get that concentration of which it is unknown. Okay, so that's the importance of that standard solution. The standard solution here is the sodium carbonate. It's going to help us get the concentration of who? Of the nitric acid. That's what we're doing here. That's what we're doing. That's back titration. That is what we call titration. So HNO3, HNO3. The number of moles of HNO3, if you cross multiply like that, guys, you are going to get 0,040 239 moles. These are the moles here. Can you see that? But these are the ones that are titrated. Ne? Let's just indicate here. These are titrated. Titrated, which means that the ones that reacted in titration. But guys, I want you to highlight this. This is in 50 cubic centimeter. In 50 cubic centimeter. Because remember, we took that 50 cubic centimeter. We took the 50 cubic centimeter, we reacted it here during titration with the standard solution. So the number of moles that I'm getting now are for 50 cubic centimeter. They are for 50. So it's important to highlight that these number of moles are in 50 cubic centimeter. The number of moles of HNO3 are in 50 cubic centimeter. They are in 50. They are in 50. Okay. Now, let's do this now. Let's do this. These are the number of moles, guys. Those are the number of moles in 50 cubic centimeter. But I ask myself now, the most important question here that you'll ever ask yourself is, again, these ones are in 50 cubic centimeter. Yes, we agree. But what are the number of moles in the big question here? We are looking for, we are looking for number of moles. This is important information. In what? In 200 cubic centimeter. We don't care about 50 cubic centimeter, guys. We have got a number of moles in 50 cubic centimeter, which is 0,040239, right? But we are looking for, this is what we're looking for. We're looking for the number of moles in 200, not in 50. So what I'm going to do here, I'm going to say 200 divided by 50. 200 divided by 50, né? 200 divided by 50. So in 200, the number of moles in 200, so therefore, number of moles of that HNO3 acid in 200 cubic centimeter. This is what we're going to do now. It is equal to, you divide the 200 divided by 50. You say 200 divided by 50. How many 50s are in 200? Because in 200, guys, 200 is our original one. Remember this, né? Remember this. We said in the beginning, from the beginning, a 13-gram impure sample of potassium hydroxide is initially dissolved in 200. That's our initial. So we're looking for the number of moles in excess, but in the initial beaker, not in 50. Not in 50, guys, but in the initial beaker, which means in the, which beaker we're talking about? This beaker here, the first beaker. So this is the first beaker that we're talking about. So this beaker here, the first one, has a volume of 200. Remember, I wrote this down. I said the volume here is 200 cubic centimeters. So we want the excess nitric acid in this beaker here, not in 50, not in 50. Okay, so that's why we call it back titration. Back, we're moving back to the original beaker. But to move back to the original beaker, which means we're going to say now that I've got the number of moles in 50. These are the number of moles in 50 here. In 50 here. I don't want the ones that are in 50, but I want the ones that are where are in 200. So I'm going to say the number of moles of nitric acid in 200 cubic centimeter is going to be 200, right? 200 cubic centimeter divided by 50. All right? Times who? Times this number of moles that I got here. The number of moles that I got here times 0,040,239. Guys, I swear to you, if you understand these calculations that we're doing now, there is no calculation in Acids&Bases that will challenge you. That's why we started with this question here. If you understand this here, even if you don't understand 100%, but as we are doing past papers, it will become easier and easier. And in the exam, you will be so confident, okay? So let's continue now. 200 divided by 50, it's 4, right? So I'm going to say 4 times 0,040,239. Guys, let's talk. Do we understand why we're dividing 200 divided by 50? Let's talk. Do we understand why? Are you still here, guys?
Yes,
sir.
Yes. Do we understand why? Yes. Do we understand why we're dividing 200 divided by 50? Do we understand the reason behind that?
So was it because we
So I
took
said,
it from...
Yes.
No, you can continue speaking, sir.
Yeah, answer the question. I think you had an answer, so you can answer.
So I was saying, is it because we took it like from the original one that they gave us, like from the A equation that we extracted from B?
Yes. So the reason is because we took it from the original beaker. The original beaker, they said it is 200, right? So we want the concentration, the original concentration in the 200, not in the 50. Because remember, we took the 50 of the one that is in excess. The one that is in excess is 50 cubic centimeters. We took it, then we titrated it, okay? Then after titrating it, we got the number of moles using the standard solution. So the standard solution helped us to get the number of moles of this excess in 50 cubic centimeters, okay? Now that we've got the number of moles of this excess 50 cubic centimeter in 50 cubic centimeter, now that we've got the number of moles, we say we don't want the number of moles in 50 cubic centimeter, but we want the number of moles in the original beaker, the first beaker. The first beaker is how many, what's the volume of the first beaker? The volume of the first beaker is 200 cubic centimeter. So we're going to say, oh, as for me, I have the number of moles in 50 cubic centimeter. It's 0.04239 in 50 cubic centimeter, but I want the number of moles in 200. So it means I will have to say, oh, 200 divided by 50, all right? Then it's going to be 4. It's going to be 4. Then 4 times this number of moles. They are going to give me the number of moles in 200 cubic centimeter, the number of moles of the nitric acid, the one that is in excess. Okay. So 4 times this guy here. I'm continuing. 4 times that. If I multiply there, I get 0.160, 160,956 mole. Okay, and I'd like to say in 200 cubic centimeter in the original beaker. In the original what? Beaker. The original beaker. Okay. These are the number of moles that I'm given there. Those are the number of moles that I'm given. And these are the ones that are in excess. Okay. Number of moles, please indicate here in excess. In excess, where? In 200 cubic centimeters. The ones that are in excess in 200 cubic centimeters. But the ones that are in excess in 50, guys, it's these ones here. The ones that are in excess in 50, it's 0.04239 moles. Okay? These ones are in excess in 50. In 50. Excess in 50 cubic centimeters. But the ones that are in excess in 200, it's these ones here. 0.16956 mole. Let's use our master formula now. Please memorize this formula by heart, with your soul. With your soul. Let's use our formula. Our formula says, this is our formula here. It says the number of moles. It says the number of moles. Let me increase my thickness. The number of moles that have reacted. That is reacted is equal to the number of moles initial minus the number of moles excess. The number of moles that are in what? Are in excess. The number of moles that are in excess. The number of moles that reacted is equal to the number of moles initial minus the number of moles excess. Of course, here, guys, you must remember, we're talking about the acid here, which is HNO3. Also here is HNO3. You can't plug two different things here, please. You can't plug two different things here. So it's HNO3. HNO3. 3. From here, guys, you can find out what you're missing. Ne? You find out what you're missing here, what you don't have. You find out what you don't have. Do we have the number of moles that reacted of nitric acid? We don't have this one. So I'm going to indicate the ones that we don't have in green. So I'm going to say this one, we don't have this one. We don't have that one. Eh? We don't have. Do I have the initial one? Yes, I have the initial one. What is the initial one? I want you to go back to the question. Let's go back to the question. They say that determine in question 5.5.1, guys, this is where we're going to get our initial number of moles. The ones that are in the first beaker, initially in the 200 cubic centimeter, the number of moles of nitric acid, initially in the 200, in the first beaker. Okay, so let's get those number of moles. 5.5.1. So I'm going to say 5.5.1 here. What am I going to say? What are we given? We're given in the initial beaker, guys. A 13 gram of impure sample of potassium hydroxide is initially dissolved in a 200 cubic centimeter. So that's the volume there. That's the volume of a 1,2 mole per cubic decimeter. That's concentration. The 1,2 is the concentration. So I'm going to say here the number of moles. Number of moles is equals to CV. Number of moles equals concentration times volume. So these are the number of moles initial. So let me indicate here. Initial of who? Of the HNO3. So let's continue now. The number of moles initially of that HNO3, HNO3 is equal to concentration times volume. What is the concentration, guys? I hope you can see the concentration. The concentration is 1,2. What is the volume? 200 cubic centimeters. So it's 200 divided by 1,000. Please always convert that. 200 divided by what? 1,000. Divided by 1,000. What is that, guys? The initial one, we are going to get it. So it's 0.24. 0.24 moles. These are the ones that we have initially in 200 cubic centimeter, guys. It's 0.24 moles. These are the ones that we are having initially dissolved in a 200 cubic centimeter of air. So the first beaker is 200 cubic centimeter. That's the initial peak. So the number of moles that we are having there is 0.24. So I'm going to plug it in the master equation. This is our master equation here. So I'm looking for the number of moles that have reacted. Let's write it. The number of moles that have reacted, okay, of HNO3 is equal to the number of moles initially, guys. We just got it now. The initial one in 200 cubic centimeters. We were told, all right? So we were told that there was the 200 cubic centimeter and then there was 1,2, which is concentration. So we had to multiply those and we got 0.24. We just got it now. 0.24. That is initial, guys. Minus the one that is in excess. Excess in 200 cubic centimeter. Can you see everything in this equation is happening in the first beaker initially in 200 cubic centimeters. So the number of moles that are in excess, which ones? We got it now. Ne? We just got it. We calculated them. Remember, we did calculate them. These ones here. Can you see this? Can you see this? This here. Those are the number of moles in 200 cubic centimeters. The ones that are in excess in 200. Okay, what are those? It's 0.160. 0.160. 0.160. Please round off to 40 decimal place of or more, ne? Or 5. 0.160. 956. 956. From here, guys, we get those number of moles here. We subtract. If we do subtraction, if we do the subtraction here, what are we going to get? We're going to get 0.07, 0.07 90.44 moles. These are the ones that have reacted, guys. But I want you to ask yourself, reacted with who? This is the most important question. The question that will help you get a distinction in the exam. The question that will help you get the distinction in the exam. This nitric acid here, reacted with who? Reacted with who? Please ask yourself this question. Reacted with who? We're looking at the first equation. Look at equation A now. Let's go to equation A. Look at equation A. Look at equation A, the first equation. Can someone answer this now? What is the nitric acid reacting with in the first equation? What is it reacting with? Look at the reactants. The nitric acid is reacting with who? Please answer. Equation A, guys. Look at equation A. What is the nitric acid reacting with?
Is it not reacting with potassium hydroxide?
Yes, it's reacting with the potassium hydroxide. So we're looking for the number of moles that have reacted with the potassium hydroxide. So it reacted with who? The number of moles that have reacted is 0.0944. But reacted with who? Reacted with who? It reacted with the potassium hydroxide. So I'm going to do a stoichiometric ratio here. I'm going to do a stoichiometric ratio. Look at this now. Look at this. So it reacted with who? We know that, oh, they're saying H, NO3 versus the potassium hydroxide. It's the second equation. It's the second equation. It's the first equation. First equation. This is equation A. Let me indicate here. Equation A. That question is for equation A. Okay? So the nitric acid reacts with the potassium, the caustic potash, the potassium hydroxide. Okay? So the other name for potassium hydroxide is the caustic potash. Yeah. Okay. So the potassium hydroxide here, we don't know the number of moles, but we know the ratios. Ne? What are the ratios there? The molar ratios. Can you see that is 1:1? It is 1:1. So it means that they've got the number of moles. You don't have to calculate the number of moles. They've got the number of moles. But let's just write it in case, ne? So that we don't lose any marks. So it's 1:1. Okay. Do we have the number of moles of potassium? No, we don't have. Potassium hydroxide we don't have. But we never. Do we know the number of moles of the acid? Yes, we have. It's 0.07944. We cross multiply now, guys. Now we get the number of moles of potassium hydroxide that reacted of the pure one that reacted. The pure one that reacted. So potassium hydroxide. Let me do this. The number of moles of potassium hydroxide, of which is pure, the pure one. Remember, potassium hydroxide, we had the impure that we put in here. I want you to remember this. Remember, we said, look at the first peak. Please focus, guys. Look at the first peak. In the first peak, I would say 13 grams of impure potassium hydroxide is added to the peak. I say to you, only the pure will react. It will react with who? It will react with look at equation A. It will react with nitric acid. So the one that reacted here, it is the pure one, which is the one that we are having now, which is the one that we are calculating now. Okay, the one that we're calculating now. So the number of moles of this one that is in pure here, the pure one that reacted, it is 0.079044 moles. 44 moles. Just like that, guys. Then, because we're answering this question here, because the question that we're answering is question 5.5.4. Calculate the percentage purity. That's why we're doing this, guys. So 5.5.1, we did answer it. We're just getting the initial one. We just did it on the side here, the initial, and that was only 4 marks. Ne? The amount, yes, it was only 4 marks. It was only 4 marks, all right? The conversion answer and the formula. So that was only 4 marks. That was the initial. Ne? 5.5.2, define a standard solution. I told you what is the meaning of standard solution. A solution of known concentration. You can't forget that, guys. It's 2 marks. You can't forget that. What is the neutralization point? Neutralization point, you can say a point where neither the acid or the base are in excess. That is the neutralization point. It's a point where neither the acid or the base are in excess. Now, 5.5.4, we are trying to calculate the percentage purity here. That's what I'm trying to show you. Calculating the what? The percentage purity. After this lesson, I am going to send you this document. You practice this. You practice the steps. So that what we are going to do tomorrow, you've got ideas. You've got ideas. If you master this, then you've mastered Acids&Bases. I hope you hear me. I hope you hear me. Okay? So if you master this, you've mastered Acids&Bases. You'll get a total in the exam. You'll get a total in the exam. Okay, so 5.5.4. Calculate the percentage purity of the potassium hydroxide. Guys, to calculate the percentage purity, we know that percentage purity is, what is the formula for percentage purity? It is the mass of the pure over the mass of the impure. Can you see this? And here, I told you guys here, that is the number of moles of potassium hydroxide. These are the ones that are pure, right? These are the ones that are pure. From here, let's get the mass, because we are looking for percentage purity. And the formula for percentage purity is the mass of the pure sample divided by the impure sample. Now I've got the number of moles of the pure. I must get the mass. It means I must get the mass. Huh? Yeah, that's what it means. Yes. Therefore, number of moles is equal to mass over the molar mass. Therefore, I cross multiply. Mass is equal to molar mass times what? Yes. Yes, mass is equal to molar mass times the number of moles. Yes, if you cross multiply like that. So mass is equal to, what is the molar mass of potassium hydroxide, guys? If you add, I think potassium hydroxide from the periodic table, you must have a periodic table on your side every time you are attending. So what is the molar mass of potassium? I think it's 39. Eh? I think it's 39. 39 plus 16, which is oxygen, plus 1. Oops, is it 39? Please check, right? Please check. Okay. Is it potassium hydroxide that we're reacting with here? Yes, it's potassium hydroxide. It's fine. It's potassium hydroxide. So what is the molar mass of potassium hydroxide? The molar mass, if I can calculate there. Yes, it's 56, guys. It's 56, ne? Yes, yes. Thank you very much. Thank you very much. It's 56. So I think it's 39 here, plus 16, plus 1. I think it's 56 there. If you add the molar mass, so it's 56 times the number of moles. We have got the number of moles here. Okay, those number of moles is it's 0.0794. So can you multiply there? 56 times those number of moles. $56 times the number of moles. I think it's 4, what? 4.42, right? 4264. 6464 gram. Perfect. This is the mass of the pure, guys. The mass of the pure. The pure mass. Pure.
So,
right? Therefore, we get the what now? What do we get now, guys? Yeah?
So would it be incorrect if I rounded the answer off to 0.08? Because my answer here is 4.48 grams.
Okay, you were not supposed to round off. You rounded off to how many decimal place?
For the previous answer, I rounded it off to 0.08, so 2 decimal places.
0.08. Okay. Don't round off. Don't round off. Just round off to 5 decimal places.
Okay.
Are going to in the exam center to mark you down, correct? Yeah. So always round off to 5 decimal places so that your final answer is more accurate.
Okay, sir.
You see here what I round off to 1, 2, 3, 4, 5. Yeah, to 6. So yeah, round off to 5 or 6. Just
Okay,
that.
sir.
Even in the labs, when we're in the labs, we usually round off to 5. Yeah. In the labs, we also round off to 5. So that's very important. All right. So this is the mass of the pew. You know from grade 11, that percentage purity is equal to the mass of the pew divided by mass in pew. The one the one that is in pew, the one that doesn't have things that we want, right? The one that is containing things that we don't want is the one that is in pew. And then times what, guys? Times 100, okay? Times 100. Do we have the mass of the pew? Yes, we have the mass of the pew. It is 4,426,464 divided by the mass of the impure. They will always give you most of the time. See, they give us in the question. Let's look at the question. In the question, 13 gram. Can you see? It's always a bigger number. 13 gram. Perfect. Because they said a 13 gram impure sample of potassium hydroxide. Can you see, guys? I find these calculations very interesting because the steps are the same. So what is this here? 13 times 100. What is that, guys, if I multiply? I think I'm getting 34,05%. So this is the percentage purity here. Yes, it's percentage purity of potassium hydroxide. It is we have only 34,05 that is pure. So if you subtract from 100 minus 34,05, you will get the impurities, the ones that we don't use, the ones that we don't want. 100 minus 34,05, you will get the impurities. Okay, so we finished the question at exactly 9 o'clock. At exactly 9 o'clock, but I'd like to summarize this. I'd like to summarize this so that you understand. I'd like to summarize this. Tomorrow we're going to be doing more past papers. Okay. Just before the end of the month, you will be masters of this. Okay. Let's see. Peji, are you here? Mashatsi, are you here? Who else
Yes,
also?
sir. We left, sir.
Okay. Oh. Okay. So the summary says, back titration is a method where concentration of the analyte is determined by reacting it with the unknown amount of excess reagent. The remaining excess reagent is now titrated with another second known concentration, which is what we're doing here. In the beginning, we had what? We had 13 grams of impure potassium hydroxide. We put it in the beaker. And then in that beaker, we had that nitric acid there. We have that nitric acid. We know that the nitric acid will react with the potassium hydroxide. But then there's a small amount of nitric acid that is going to remain in the beaker. We take that small amount, which is in excess. In excess, it's 50. It's the one that is remaining. 50 cubic centimeter is the one that is remaining. We take that 50, guys. Oops. Yes, we take that 50, we titrate it. We put it with titration. This is titration here. We react with titration, we're just taking that excess. We react with what? The standard solution, the one that we know its concentration. Standard solution is sodium carbonate here. We know its concentration. They gave us the concentration. They even gave us the volume and the concentration. What was the volume and concentration here? They said it's 23.67. That's the volume. And the concentration is 0.85. So they gave us, that is the standard solution. That standard solution, guys, is going to help us. It's going to help us. It's going to help us get the concentration of nitric acid. How is it going to help us? Firstly, we're going to get the number of moles of sodium carbonate. Number of moles because CV is 0.85 times that. We get those number of moles. Then we do the stoichiometric ratio. We do the stoichiometric ratio. We find the number of moles of nitric acid. After finding the number of moles of nitric acid in 50, remember, keep that in mind. It's in 50. It's not in 200 because 200 is in the original. We want in 50 here. So in 50, it's 0.4239 moles. Okay? Ask yourself, I've indicated here in this circular thing, we are looking for the number of moles in 200 cubic centimeter, not in 50. Not in 50, please. Not in 50. So in order to get the ones that are in 200, we're going to say number of moles in 200 is equal to 200 divided by 50 times 0.4239. So I'm going to get 4 times that. Then we get the number of moles in excess in 50, not in 200. Okay? Then we use our master formula. Our master formula says number of moles that have reacted, which we don't have, is equal to the number of moles initially. We had to calculate the number of moles initially there because the first question said calculate the number of moles initially minus the number of moles in excess, which is the one that we got now, right? The one that we got now. So the number of moles that have reacted is nitric acid. It's 0.24 minus 0.1695. We subtract them. The ones that have reacted, it's 0.07944. But ask yourself, reacted with who? You always ask yourself. It reacted with the potassium hydroxide, the caustic potassium hydroxide. So we get the number of moles of potassium hydroxide that have reacted because we know that only the pure reacts. The impure one doesn't react. Only the pure react. So we get the number of moles of potassium hydroxide that have reacted. So it is, if you cross multiply there using the stoichiometric ratio, you get 0.07944. Then from there you get its mass. Then from getting the mass, you now calculate the percentage purity. Then you get the percentage purity as 34.05%. 34.05%. Did we understand this? Okay.
Yes, sir.
I hope we did understand this. Yes. So I'm going to send the document in the group so that you do it again. You do this question again. Okay. If you master this question, guys, there is no question that will be a problem. That's why we started with difficult questions. I didn't want to introduce Acids&Bases, start from basics and stuff. No. We'll do that the other day. Of course, we'll do it. We will do it. I want to start with these challenging questions so that in the exam you are confident. Okay, right.
Yes.
I think I'm going to end here. And then
Sorry, sir,
tomorrow
one more question.
We're going to do another. Yes.
Sorry, sir, one more question before we end. What's the difference between, let's say, when we were calculating the number of mole, what difference would it make if we just used the mole ratio of each compound in the original formula?
Okay, can you repeat the question? I think in the beginning it was cutting a little bit.
I was asking what difference would it make if we used the mole ratio instead of calculating the number of mole from the original formula?
or from the original formula.
Yes, sir.
Yeah, that will make a big difference. Ne? That would make a big difference because the stoichiometric ratio, let's see, here we had like 1:1. We had the stoichiometric ratio of 1:1. If we had 1:2, then the number of moles would be different. In this case, 1:1, guys, we get the same number of moles. So there was no need to do the stoichiometric ratio here because it's 1:1. But let's say it was 1:2. This was going to be necessary. Okay.
No, I
so
see.
in this case here, yes, in this case there was no difference that was made. There was no difference that was made here because the ratio is 1:1. And there was no need to do the stoichiometric ratio here because it's 1:1. When you know that the ratio is 1:1, you just know automatically that the number of moles are the same. But always do the stoichiometric ratio. Did I answer your question?
Yes, sir, you did. Thank you.
Okay. So I'm going to end the lesson here. Tomorrow we're going to do more calculations and more calculations. Okay. This question, guys, is from IEB. IEB. 2021 June. IEB May June paper. Not NSC. You guys are doing the National Senior Certificate. This was the most difficult question in the IEB. Not most difficult, but just required more steps. And I know that if you understand this, you'll conquer in the exam, okay? It was tested, this question, exactly a copy of this question was tested in Mpumalanga. I think Mpumalanga 2025, okay? They put this question here, and the students got a biggest shock of their lives, okay? Yeah, so, but if you understand this, you'll be fine. Let me send you this document on WhatsApp. Can we end the lesson now?
Yes, sir.
All right, so let me do this here. Yes, so yeah, thank you for attending. Bye-bye.
Thank you, sir. Bye.
Vui, did you understand? Because I think you were quiet, or you were talking. Voye, are you here? Voye, let me react to Voye. Voye, can you hear me? Voye. Okay, Voye cannot. Okay, I will touch it on WhatsApp. Okay, bye bye.